NANI?!
Good day everyone. So we're here to discuss what is Coulombs law. In here, we have our objectives for today. Number 1. Explain Coulombs law and identify the factors that affect the electrostatic force between two charged objects. And second, apply Coulombs law in solving real-life problems and practical scenarios. So Coulombs law describes the electric force between two charged objects. It states that the electrostatic force, or F, between two charges is directly proportional to the product of their charges, and inversely proportional to the square of the distance between them. So in here, we have our formula. It is F is equals to K times Q1 times Q2 over R squared, where F is the electrostatic force or magnitude. It refers to the force acting between two charges occupying the same space. If the charges are unlike, one positive and one negative, the force is attractive. The charges move closer together. If the charges are the same, both positive or both negative, the force is repulsive. The charges move away from each other. And even neutral objects can be affected, although the electrostatic force on them is usually weaker. Then, we have our Q, which is the charge in coulombs. It represents the amount of electric charge. The greater the value of the Q1 and Q2, the stronger the electrostatic force. Then we have R or D, which is the distance in meters. This is the distance between the two charges. The electrostatic force is inversely proportional to the square of the distance. Closer charges is equals to stronger force, farther charges is equals to weaker force. This is called the inverse square law, similar to the law of gravity, which is why distance is very important. And lastly, we have our K, or the Coulombs constant. This is fixed value used in formula to calculate electrostatic force. K is equals to 9 times 10 raised to 9 n m squared over c squared. It can also be written as 8.99 or 8.88 in some lectures. So now, let's focus on the factors that are affecting the electrical force and how they influence its magnitude. These are 1. Magnitude of charges. It is the Q1 and Q2. The force is directly proportional to the product of the magnitude of the charge. Its effect is if either charge increases, the force increases proportionally. For example, doubling one charge doubles the force. Doubling both charges quadruples the force. And then number 2, distance between charges, or the D, or R. So the force is inversely proportional to the square of the distance between the charges. Its effect is if the distance doubles, the force is reduced to 1/4. If the distance is halved, the force increases 4-fold. Number 3, medium between charges, dielectric constant, or the K. The force depends on the material between the charges through its dielectric constant, which modifies the permittivity in the force equation. In a vacuum, K is equals to 1, but in other materials, K is greater than 1. Its effect, a higher dielectric constant, reduces the force between charges. For instance, placing charges in water, which has a high dielectric constant, decreases the force compared to the same charges in air. Lastly, number 4, nature of charges, or the sign of Q1 and Q2. So like charges, both positive or negative, repel each other, which unlike charges attract each other. So the effect, while the magnitude of the force remains the same, the direction of the force, or the repulsive or attractive, depends on the sign of the charges.
So this is how electrostatic air purifiers work using the principles of Coulombs law. Electrostatic air purifiers remove dust and pollutants from the air by using electric charges. In the device, dust particles are given a negative charge and are then attracted to metal plates that are positively charged. This movement is caused by an electrostatic force, which is described by Coulombs law, the law that defines the force between two charged objects. So let us look at a quick example. A dust particle is charged with negative 1.0 times 10 raised to the power of negative 9 coulomb, and the metal plate has a charge of 1.0 times 10 raised to the power of negative 6 coulomb. So the distance between them is 0.01 meters. Using Coulombs law formula, we will substitute the values. So after we substitute the values, we will get the answer 0.09 Newton. So this force pulls the negatively charged dust particle toward the positive plate. So as shown here, in the illustration, the negatively charged dust is drawn to the positive plate, effectively cleaning the air. This is how electrostatic purifiers use simple physics to improve air quality.
Now, let's take a look at an application of Coulombs law in calculating electric field and electric potential. Coulombs law is essential in electrostatics. It allows us to calculate the electric force between charged particles, and it's a key tool in determining electric field intensity and electric potential, two fundamental concepts in electric engineering and atomic physics. Let's work through an example involving 2-point charges. We have Q sub 1 equals positive 3.0 times 10 to the negative 6 coulombs, and Q sub 2 equals negative 2.0 times 10 to the negative 6 coulombs. They are separated by a distance of 0.05 meters. Step 1. Calculating the electric force. We'll start with the Coulombs law, which states F equals K times the absolute value of Q sub 1 times Q sub 2 divided by R squared, where K is 8.999 times 10 to the 9th Newton meter squared per coulomb squared. Substituting the values, F equals 8.999 times 10 to the 9th multiplied by 3.0 times 10 to the negative 6 multiplied by 2.0 times 10 to the negative 6 divided by 0.05 squared. This will give us electric force between the charges. Step 2. Calculating the electric field at Q sub 2. Next, we calculate the electric field E at the position of Q sub 2 due to Q sub 1. We use the formula E equals K times Q sub 1 divided by R squared. Plugging in the values, E equals 8.999 times 10 to the 9th multiplied by 3.0 times 10 to the negative 6 divided by 0.05 squared. This gives us E is approximately 1.08 times 10 to the 7th newtons per coulomb. So that's the electric field intensity at Q sub 2 due to Q sub 1. Step 3. Calculating the electric potential at Q sub 2. Finally, we calculate the electric potential V at Q sub 2 due to Q sub 1. The formula is V equals K times Q sub 1 divided by R. Substituting the values, V equals 8.99 times 10 to the 9th multiplied by 3.0 times 10 to the negative 6 divided by 0.05, which gives us V is approximately 5.39 times 10 to the 5th volts. So, the electric potential at that point is around 539,000 volts. In summary, using Coulombs law, we calculated the electric force, field, and potential between 2-point charges. This kind of analysis is crucial in many fields, from designing electronic components to understanding how atoms interact in matter.
Are you ready for some practice problems? Here we go!
For the problem 1, we are given that two small spheres are 0.2 meters apart. One sphere has a charge of 4.0 times 10 to the negative 6 coulombs, and the other has charge of 6.0 times 10 to the negative 6 coulombs. Our goal is to find the force between them. We will use Coulombs law, which states F equals K times Q1 times Q2 divided by R squared. Here, R is the distance between the charges, which is 0.2 meters. K, the Coulomb constant, is 9 times 10 to the power of 9 Newton meter squared per coulomb squared. Q1 is 4.0 times 10 to the negative 6 coulombs. Q2 is 6.0 times 10 to the negative 6 coulombs. Now, let's plug in the values. F equals 9 times 10 to the power of 9 Newton meter squared per coulomb squared, multiplied by the quantity 4.0 times 10 to the negative 6 times 6.0 times 10 to the negative 6 divided by 0.2 squared. Multiplying the charges gives 4.0 times 10 to the negative 6 times 6.0 times 10 to the negative 6 equals 2.4 times 10 to the negative 11. And squaring the distance, 0.2 squared equals 0.04. So now we have F equals 9 times 10 to the power of 9 multiplied by 2.4 times 10 to the negative 11 divided by 0.04. Then 2.4 times 10 to the negative 11 divided by 0.04 equals 6.0 times 10 to the negative 11. So now, it simplifies to F equals 9 times 10 to the power of 9 multiplied by 6.0 times 10 to the negative 10. And by multiplying this, we will get an answer of F equals 5.4 newtons.
Today, I will present the solution to a problem involving 2-point charges and the computation of electric potential, potential differences, and work. So now, let's read the problem. Point charges of positive 16 times 10 raised to negative 3 and negative 16 times 10 raised to negative 3 are placed 20 cm apart. From A to B and C to A in the absence of friction and with no increase in kinetic energy. So now let's answer the questions. Compute the potential points A, B, and C. Using Coulombs constant K is equals to 9 times 10 raised to 9 nm squared over C squared, the electric potential at a point is calculated by the formula V is equals to K multiplied by first charge over R1 plus second charge over R2. At point A, the distance to the charge are 25 centimeters and 5 centimeters. After substituting into the formula, the potential of A is found to be approximately negative 2.304 billion volts. At point B, which is equidistant from both charges, the potentials due to each cancel out, giving a net potential of 0 volts. To solve the point C using respective distances of 14 centimeters and 6 centimeters, the potential comes out to be approximately negative 1.372 billion volts. Next, we can calculate now the potential differences between A and B. And to get the potential difference between A and B, just subtract V sub A to V sub B and we will get the answer of negative 2.304 billion volts. While getting the potential difference between B and C, we will get positive 1.372 billion volts. Now for the last question, how much work will be required to move a point charge of 11 times 10 raised to negative 3 from A to B and C to A in the absence of friction and with no increase in kinetic energy. So the work required to move a test charge of 11 times 10 raised to negative 3 is... So from A to B, we will get negative 25.34 million joules, and solving C to A, we will get negative 10.26 million joules. This means energy will be released in both moves since the potential is decreasing. Thank you.
It's activity time. Are you ready? Since you already learned how to solve some basic Coulombs law questions, it is now the right time to try it. For your activity 1, try answering this. You may pause the video while answering. Now, here's the answers. Try to process how did this happen. And for your activity 2 and 3, you may try answering this too without having some key to correction. Now, here's the references that we've used. You might want to check it too. Here are the members of GL. Lastly, thank you! We really hope that you learned something good today. Goodbye!